So good morning, everyone. I am Émilie LAFFONT, and today I hope that I will help you to gain an understanding about my thesis, whose title is The Development of a Plasmonic Transducer for the Detection of Biological Species. The goal of my thesis is to develop a biosensors whose transducer is based on surface plasmon in order to diagnose diseases such as the famous COVID-19. And to do that, I need to combine two fields of expertise. The first one is relative to the production of diffraction gratings that I use as couplers and as the base for my detection surface. And the second one concerns the functionalization of these gratings in order to selectively capture the targeted biological molecules, such as antibodies, antigens, depending on the chosen application. But before delving deeper into the details, I will briefly explain the concept of surface plasmon at the heart of my thesis project. So a surface plasmon is an evanescent wave propagating along metal dielectric interface, which is very sensitive to the environment bounding this interface along which it propagates, and especially it is sensitive to the refractive indices respectively associated with each medium of this interface. And in my case, the metal is a thin gold deposition that I do on the top of my gratings, and the analyte, also called dielectric and represented in yellow on the diagram on the right on the slide, is the diluted biological fluid that I inject from my detection device. So a number of biosensors base their detection method on the surface plasmon resonance. This phenomenon is a transfer of energy from the incident being just there to the plasmonic mode, which manifests through a dip in the reflectivity spectrum of the zeroth order, also called the Fresnel reflection. And you have an example just there considering the water as analyte, because one has to notice that the value of the resonance angle depends on the analyte chosen during the experiments. So if I replace the water covering my thin gold layer by a mix of glycerol and water, so with a higher refractive index, this resonant tip has shifted to the right because of the high sensitivity of the plasmonic mode, and because of the high sensitivity to the refractive index along the metal dielectric interface. And so to determine if there is a change of refractive index, such sensors assess the shift in this resonance angle. And this is a principle widely used for biosensing. But in the case of my thesis project, the configuration and our approach is a little bit different because in practice, we produce corrugated gratings with a high depth period ratio and a period smaller than the wavelength, the incident wavelength, And so the interaction of this incident wavelength with our gratings results in two propagative orders, the zeroth, which is represented on the right on this slide, and the minus first orders, and the combination of their angular spectra of intensity features a switch pattern, which is illustrated just there on the right on the slide, with two working points called theta L and theta R, where the intensities respectively associated to the minus first order and the zeroth order are equal. And so, unlike the classical SPR biosensor, the switch measurements consist of an intensity measurement, and thus you can see, for example, here that if you consider the switch pattern represented in pink, it is a little bit different compared to the blue one, because the blue one was measured for water and the pink one is associated to the measurement for the glycerol water. And so if I fix my incident angle at theta R here, you can see that the differential measurement is no more 0, but it is positive, and so it means that variation of refractive index was detected. And to obtain such measurements, I use a setup comprising a laser diode with the number 1 here, whose beam locally probe my grating, which is inside a container, inside which fluids are injected thanks to PIC tubings connected to syringes. And when the angle of my incident beam from the laser diode is fixed at theta r or theta l, as this is illustrated on this slide, I can check with 2 photodiodes here with the number 4 and 5 that the intensities respectively associated to the 0th order with the reflected beam in red and the refracted beam for the minus first orders in gray, that their intensities are equal. And after that, I can change the solution injected inside my detection device, and thus I can measure the variations induced by this change of solution for each order. The advantages of this kind of setup is that it is rather easy to implement. It gives access to differential measurements, so we can cancel all the common fluctuations between these 2 orders, and it is really, really sensitive. So to date, I obtained 2 kinds of results by this way, and you have an example here. It's about sensing centrogram. So just I will just say to you that I didn't put the whole scales on the left of my diagram, just because I didn't publish yet about that, but it's just to give you an idea. So what I do is that I fix my incidence angle at theta L, and I basically, after that, injected different solutions. So the solution number 0 is my reference solution and was no more than water. And as you can see, each time that I injected it, so at the beginning of this sensorgram and at the end, I obtained a differential signal of 0. But each time that I injected after that the same number solution other than 0, I obtain the same level stage. So here and here for the number 1, for example, you have more or less the same level, and here for the level 2, it's the case too. So it demonstrates a good repeatability in our detection process. And last but not least, if you check the level stage represented in orange, which represents the refractive indices of the solutions that I injected, you can see that they match very well with the differential signal that I measured. So it demonstrates a good correlation between the differential signal that I measured and the refractive indices of the solutions that I use inside my detection device. So the results that I just presented are rather promising, and the next step would be to focus on functionalization strategies, just like these illustrated on this slide, in order to, in a final step, apply our detection process to a real application, like the detection of the famous COVID-19. And thus maybe offer an alternative to the current RT-PCR tests. So, oops. Thank you for your attention, and if you have any question, it will be a pleasure to try to answer them. Thank you.